We are in section 4.3, complements, conditional probability, and Bayes' theorem. Computing at least probabilities typically uses the complement rule, what we discussed last time. And the phrase at least means greater than or equal to. So the big one that we focus on is going to be at least one. And so the probability of at least one occurrence at least one occurrence of event A. And using that complement rule, we're going to have it's going to be equal to 1 minus the probability of no occurrences of event A. So the next example that we have says among Americans who consider themselves to be avid bakers, 59% say that their favorite item to bake is cookies. Suppose that 4 avid bakers are randomly selected. What is the probability that all 4 say their favorite item to bake is cookies? And so we have the probability of all 4 say cookies is their favorite thing to bake. And for this, we're going to say that these people are all independent of one another. Whenever we deal with people, they are independent of one another. The only time that they are dependent is if we are selecting maybe 2 people, and those people are maybe it's a couple, and so you would have to select the spouse, or if it's like a mother and their children, you would have to select the ones that match up with them. Another instance of them being matched or dependent data would be if we were involving twins or something along those lines. So the first one here says the probability that all 4 like to bake cookies is going to be the probability that the first person likes to bake cookies, which is going to be 59% or 0.59. The probability that the second person likes to bake cookies, which is 0.59. Third person likes to bake cookies, which is also 0.59. And then the fourth person likes to bake cookies, and that's 0.59. Another way to write this is 0.59 to the 4th power. When you multiply this all out, you get 0.1212. Again, rounding our probabilities 4 decimal places. Part B says what is the probability that none will say their favorite thing to bake is cookies. And so if you think about this, the probability that you're going to be an avid baker out of this group is going to be 100, and that you like to bake cookies is 59% or 0.59. So I'm going to rewrite 100% as just 1, and I'm going to subtract away using that complemented idea 0.59. And so the probability that somebody does not, their favorite thing to bake is not cookies is going to be 0.41. And so the probability that none don't like to bake cookies is their favorite thing, so we'll say all 4 is not cookies, is going to be the probability that the first person doesn't like to bake cookies, or is their favorite thing I should say, is 0.41. And then the second one would be 0.41, the third one 0.41, and the fourth one 0.41. So I'm going to rewrite this time as to the 4th power. Multiplying this out, we get 0.0283, rounding 4 decimal places. Part C says, what is the probability that at least one, and here's that new word that we just talked about, will say that their favorite item to bake is cookies. So probability that at least one says cookies. And from up above, we're going to use the idea of the complement, which is going to be 1 minus the probability that no one's favorite thing to bake is cookies out of all 4 of those. So I'm going to write it down as all 4 is not cookies. And looking at that word at least one, that means either 1 out of those 4 people's favorite thing to bake is cookies, or 2, or 3, or 4, or all 4 of them would like to bake cookies. And the only case that we're not considering is the probability that, or the chance of, all 4 of them not liking to bake cookies. They like to bake maybe brownies or cakes or something else better. So I'm going to go and do 1 minus 0.0283, because this probability right here is exactly what we already calculated up above. Subtracting these, we get 0.9717. This is definitely a topic that students struggle with and something that you want to try to look at and practice some extra problems with. The next example that we have says the table below shows results from a ChemBio test for hepatitis C among HIV-infected patients. So if you notice, we have a table here of Hep C and no Hep C. And then we also have people that have tested positive for HIV and negative for HIV. What we don't have here is total columns and rows like we've had before, and sometimes they give them to you and sometimes they do not. The first part, though, says to find the probability of selecting a subject with a positive test result. So with a positive test result, given that the subject does not have Hep C. So, and then it says, why is this problematic? And we'll talk about that in a minute. But this is going to be the probability that we have somebody tested positive, and it's given that they have no Hep C. And so for this, we're going to go ahead and use the formula that we had from the last section. And this is going to be the number of people that have no Hep C. And in the numerator, it would be the number of people that are positive and have no Hep C. So the total number of people that do not have Hep C, you would get by adding 2 plus 1,153, and we get 1,155. So I'm going to go ahead and write total over here. And so our total is going to be 1,155, and again, that goes in the denominator. And then we have to write down the people that are positive and have no Hep C. So no Hep C and positive would just be these 2. So dividing this out, rounding 4 decimal places, we get 0.0017. Part B says, find the probability of selecting a subject with a negative test result given that the subject has Hep C. So the probability that we have a negative test result given that the subject has Hep C. So again, using the formula, we're going to go ahead and write down the number of people that have Hep C. And in the numerator, we're going to have the number of people that have a negative test and have Hep C. So again, looking at our values in our table, the number of people that have Hep C, we're going to get by adding up 335 plus the 10, which is going to be 345. And then the total number of people that have a negative test result and have Hep C is going to be 10. So dividing this out, and again rounding 4 decimal places, we get 0.0290. The next section that we have is 4.4, which is called counting. The first rule that we have is multiplication rule for counting. If a task consists of a sequence of choices in which there are P selections for the first choice, Q selections for the second choice, and R selections for the third choice, and then so on, so we can have more than just 3 choices here, then the task of making these selections can be done by multiplying P times Q times R different ways. If you can see, this value is going to be very large depending on how large of those choices that you have. The first example that we have says how many different current California license plates can be created using the standard setup, no special characters or spaces. The standard setup is going to be a number followed by 3 letters followed by 3 numbers. So we're going to have a number followed by 3 letters followed by 3 numbers. And so in here, what we're going to do is write down how many different possible numbers are there. There are 10 total. And letters, 26 letters in our alphabet, again, no special characters, and it doesn't say anything about them not repeating. And then numbers again, 0 through 9, there's 10. And then with these values, we're going to go ahead and multiply these. Let's put some multiplication dots in there. So when you multiply this out, you're going to get a very large number. We're going to get 175,760,000. And we need to put units with this, and what we're discussing here is California license plates. The next example that we have says a social security number is used to identify each resident of the United States uniquely. The number is of the form, and it's 3 digits, dash 2 digits, dash 4 digits, where each X is a digit from 0 to 9. How many social security numbers can be formed? So you can go ahead and put dashes here. So 1, 2, 3. We have a little dash. 1, 2, dash 1, 2, 3, 4. And each of these spaces is a number. And we have numbers are going to be 10 different possibilities that we have between 0 and 9. And then once you have all those 10s in there, you can go ahead and multiply them. Another way to do this would be to write 10 to the 9th power, which might be easier to put in on your calculator. When we do this and you multiply this out, you're going to get a very large number. You actually get 1 billion. This is going to be 1 billion social security numbers. Part B says, what is the probability? Remember, probability has to be between 0 and 1 of correctly guessing the social security number of the U.S. president. So the probability of the correct social security number is going to be, and the president only has one social security number, so that would go in the numerator, divided by all the different options that we have, which is that giant number that we have up above of 1 billion.
On your calculator, you're going to do 1 divided by 1 billion. If you notice, your answer is going to have an E in it. That E means times 10. So this would be the same as 1 times 10 to the negative 9th.
When you use your calculator and you divide this out, a lot of times you're going to get 1E negative 9. And this E shows up quite often, and it's a problem for you guys with putting answers in on an exam on MyOpenMath or turning in homework. They will be marked wrong. E, it means the same thing as 1 times 10 to the negative 9. So that E is equivalent to the times 10 that we have over here. The next definition that we have is called a factorial. This is denoted with an exclamation mark. If n is greater than or equal to 0 is an integer, then n factorial is n times n minus 1 times n minus 2, so on till 3 times 2 times 1. Also note that 0 factorial and 1 factorial is equal to 1. So the next example that we have says 15 students in a class are asked to line up for a class picture. How many different ways can they line up? So we have a total of 15 students here. And so we are going to go ahead and I will make some dashes. So the first student that can line up, there's only one student that we're going to select. However, I could select a total of 15 different kids to go first. And then we'll say Jimmy's already standing up there. So how many students could stand up next? And to figure that out, we already have Jimmy standing up above, so now I have 14 different students that I can select from. And then the next we have Jimmy and we'll say Rose are both standing up at the front of the class. And now I only have 13 students that I can select from. And this goes on until we get down to the last few students, so like 3, 2, and then 1. And multiplying this, again, just like how we did, I put my multiplication dots in. There's a faster way to do this. This would have been really challenging if I asked you guys how about 36 students, and you would have had to write 36 times 35 times 34 times 33 and so on, all the way down to 3, 2, 1. And so a faster way to do this is to write this as a factorial. And so again, a factorial was n times n minus 1. So in this case, it's 15. 15 times 15 minus 1, which is 14, times 15 minus 2, which is 13, and so on. So on your calculator, you get 1.308. Again, we have that e, so that's going to be times 10 to the 12th. The next thing that we have is permutations and combinations, and then how to use our graphing calculator. So a permutation is the number of arrangements of R objects chosen from N objects in which the N objects are distinct, repetition of the objects is not allowed, and our big one here is going to be order is important. So AB is going to be different than BA. We have a formula here that we don't have to stress too much about because we will be using our graphing calculator. The next definition that we have is called combinations, the number of arrangements of R objects chosen from N objects in which the N objects are distinct. Repetition of objects is not allowed, and this time order is not important. So AB is the same as BA. So they're identical with the permutations and combinations. However, permutations is where order is important, and combinations is where order is not important. Right below that, we do have a box on how to use our graphing calculator to help along with this. And you'll notice we have an NPR and an NCR, and then also an exclamation mark. So we have our permutations, combinations, and factorials. To get to this, we're going to go ahead and select our math button, and then we're going to go over to PRB or PROB, depending on which TI graphing calculator you have. And then you select whichever one of those three things that you would need to use. We also have permutations when some items are identical to others. You see this a lot when you go in and take a test. Sometimes they'll ask the same question multiple times just to make sure that you actually do understand a concept. So the number of permutations of N objects of which N1 are of one kind, N2 are of another kind, and so on. And we'll say N sub k are of the kth kind is given by, and we have N factorial divided by N1 factorial times N2 factorial times all the way through to Nk factorial. And notice that N is equal to N1 plus N2 plus, and then all the way through to N sub k. So the next part is getting us used to using our calculator. The example says find the values using a calculator. So on your calculator, I'm going to go ahead and try to work out with you guys. We'll do A, D, and E and G together. And then I want you guys to try the remaining ones on your own, and I will put the answers up.
For part A on your calculator, you're going to go ahead and type 7. And then we're going to go to math, scroll over to PROB or PRB, depending on your calculator, and then scroll down to number 4, which is the factorial. Select enter and enter one more time, and you should get your answer. The next one, part D, we're going to go ahead and type the first number that we have. Our N value is 9. And then we're going to go over to math, go over to PROB, scroll down to permutations, which is number 2, and then we're going to type our second value, which is a 0. From here, go ahead and select enter. We arrive at our answer. For G, we're going to do exactly the same thing. I'm going to go ahead and type my first value, my N, and then I'm going to go to math. I'm going to go over to probability or PROB. Scroll down to NCR for combinations, and then select 0, which is the second value that we have. Enter, and then we also get our number.
So from your calculator, we got 7 factorial is equal to 5,040. And then from the calculator, we got that the permutation of 9 choosing 0 is going to equal to 1. And then we got the combination of 9 choosing 0 is also going to be 1. Trying the remaining ones on your own. 0 factorial is equal to 1. Part E is equal to 3024. H is equal to 126. C is going to be equal to 39,916,800. F is going to be equal to 362,880. And then I is just equal to 1. The next example that we have, we're going to go ahead and circle, and we'll do that one together. The next example that we have says, in the U.S. Senate, there are 21 members on the Committee for Banking, Housing, and Urban Affairs. 9 of these 21 members are going to be selected to be on a subcommittee. So we have 9 of those 21 people will be selected for the subcommittee on economic policy. How many different committees are possible for this subcommittee? So from this, I want to ask you guys if order is important in this problem. Does it matter if you're the first one selected for that subcommittee or the 9th one selected for that subcommittee? No, it doesn't matter. So this is going to be order is not important. And so that's the first thing you should always ask yourself, is order important or not important? So since order is not important, that means that we're dealing with a combination. So I'm going to put a C there. Okay, if you remember from using the calculator previously, you have 2 numbers that we need to put in. The first number is N, and that's the total number of objects that we have. And in this case, we're dealing with people in this Senate committee, and there's 21 members, so that's our total, and that's the first number that would go there. The second value is how many of them are we choosing, and for this problem we are selecting 9 for that subcommittee. And then we're going to be able to use our calculator to arrive at the answer.
On your calculator, you're going to type in our N value, which is 21. You're going to go to Math, scroll over to PROB. This is a combination problem, so scroll down to 3 and CR. And then the value that we are selecting in this problem is 9. Select Enter. You arrive at your answer.
So from the calculator, we get 293,930 subcommittees. So the next one says, in how many ways can the top 2 horses finish a 10-horse race? So dealing with a race, order is important. So this one, order matters. And so that means that we're dealing with a permutation. So with a permutation, we have a total of how many different horses that are in the race. There are 10. And then we're going to be selecting the top 2 horses. So 2 horses.
On your calculator, we're going to go ahead and select 10, which is the total number of horses that we have. And then we're going to go to Math, go over to PROB, go down to a permutations number 2. And then we're selecting the top 2 horses to finish the race. Select Enter, and we arrive at our answer.
From the calculator, we arrive at an answer of 90 ways for 2 horses to finish. There's another method of using spaces, kind of like what we did before, in order to solve this problem. If you think about it as like the students that were lining up in the class, but this time instead of having 15, we only have 2, because we only care about the first horse and the second horse. So how many different horses could finish the race first? Yes, only one will finish it, but how many different horses had an opportunity to do that? Would be 10. And then we'll say Lucky Stripe just finished first. How many horses are still out there that could come in second? There would be 9. Multiplying those two numbers together, we do arrive at 90. So this would be a second way to do this. However, this method only works when we're dealing with permutations, when order matters. The next example that we have says, suppose that there are 55 Democrats and 45 Republicans in the U.S. Senate. A committee of 7 senators is to be selected by forming members of the Senate randomly. So we have 55 Democrats and 45 Republicans. So part A says, what is the probability that a committee is going to be composed of all Democrats? So this time we want all Democrats. So first thing is, does order matter in this problem or does it not matter? And again, we're dealing with the idea of a committee, just like we did up above. So this is going to be order does not matter. So order is not important. And since order is not important, I know that we're going to be using a combination. So this one does ask for a probability. So we do know that we're going to have a value between 0 and 1. And so in order to do a probability, we have to know our sample size or our sample space. So in order to come up with that, I'm going to call that N. I'm going to put a C because we said order is not important. When you talk about your sample, you need to look at everybody as being the same. Meaning I don't care if you're Democrat, Republican, that doesn't matter. So total number of Democrats and Republicans that we have is going to be 100. And we're going to be selecting how many of them to be on this special committee. And we have 7. I'm going to leave this as our value here. I'm not going to work this out, but this would be our denominator in our probability problems. So for this probability problem, it does ask for all 7 people to be Democrats. So that means we're going to have 7 Democrats and 0 Republicans. And so I'm going to go ahead and write down Democrats and Republicans. And above both of these, I'm going to put a C because, again, we're still dealing with order is not important. When I have this, I'm going to put my little numbers in there in just a second, but I want to talk about the word and means to multiply. So we're just going to go ahead and put a dot there. So the total number of Democrats that we have here is 55. And I am going to be selecting 7 Democrats. And then the total number of Republicans that we have is 45. And in this problem, I'm selecting 0. I'm going to divide this by N, my sample size, which is going to be 100, choose 7. And on your calculator, you can substitute this whole thing in just one shot. Some students like to do piece by piece and then put that back together that way.
On your calculator, we're going to go ahead and type this all in for one problem. And we're going to write 55. We're going to go over to math. This is for our Democrats. Go over to PROB. This is a combination. And we are selecting a total of 7 Democrats. I'm going to go ahead and hit times. And then we have 45. Go over to math. PROB. And this is for our Republicans. Still, it's a combination. We're selecting 0 Republicans. I'm going to go ahead and select enter here and get an answer. And then I'm going to divide by. And my denominator here is going to be 100 total people that we can select from. Go math. Go over to probability. Go down to combinations. We're selecting a total of 7 individuals. Select enter, and we arrive at our probability.
So from the calculator, we arrive at an answer of 0.0127. Part B says, what is the probability that the committee is composed of 3 Democrats and 4 Republicans? So this time we have probability of 3 Democrats and 4 Republicans. So I'm going to go ahead and set this up the same way. Write Democrats and Republicans. Go ahead and put a C above both of those, and a dot for multiplication above my word and. So again, Democrats, if you look up above, we had a total of 55 Democrats. And this time we're only selecting 3. And Republicans, if you look up above, we have a total of 45. And we are going to be selecting 4. I'm then going to divide this by our sample, which is going to be 100, choose 7. So again, substituting all this in on your calculator, you arrive at an answer of 0.2442. The next example, we're going to go ahead and circle and work on that one together, along with the next 2. So we'll finish page 10 all together in class.